Here we give a brief lecture on the chain rule, applying it to exponential functions. We'll explore the chain rule and demonstrate its power, particularly with exponential functions. If f of x is an exponential function of the form b to the x for some positive real number b, then we can use the definition of derivative, as done in the first part of this course, and work out that the derivative is the limit as h goes to 0 of b to the h minus 1 over h times b to the x. This limit as h goes to 0 of b to the h minus 1 over h is some constant. If b is 2, we get 0.693. If b is 3, we get 1.099 approximately. And so the derivative of an exponential function of the form b to the x is some constant multiple of this. In some cases, it might be a multiple of 693 or 1.099. We learned earlier that if we define e to be this limit, then the derivative of e to the x is simply e to the x. E is a special function where that limit on the previous slide is equal to 1, and so we don't have to worry about what constant we multiply by. With this result and the chain rule, we're prepared to differentiate any exponential function regardless of the base b. Suppose b is a positive real number. As a result of the definition of logarithms, which is the inverse of the exponential function, if you give me a positive number b, I can write b as e to the natural log of b, since the exponential function and the natural log are inverse functions. So, given an exponential function of the form b to the x, then I can rewrite this by taking b to the x as e to the natural log of b. So this expression here, b to the x, becomes this expression. And then using properties of logs, I can multiply these exponents and write it this way. So b to the x can be rewritten this way. Again, if my function is b to the x, where b is some positive real number, then I can rewrite it using the inverse function and express it this way. Then if I take the derivative of this final form here, the chain rule tells me that since the derivative of e to some power is just e to that power, then I will get e to that power times the derivative of the inside part. Well, what's the derivative of the natural log of b times x? That's just the natural log of b. And then remembering that this e to the natural log of bx was really the same as b to the x, I have found that the derivative of b to the x is natural log of b times b to the x. I got all of that by using the chain rule and my understanding of logarithms. We've used this result previously, but without proof. Until now it was magical, given without justification. Let's practice the chain rule for a moment and work with some exponential functions. Suppose we're given the function 3 to the sine x. This is an exponential function, but instead of the x in the exponent, it's something more complicated. By the chain rule, and the fact that the derivative of the exponential function 3 to the x is the natural log of 3 times 3 to the x, then we know that the derivative of this function is natural log 3 to the, well, that's a sine x, not an x, so we have to multiply by the derivative of sine x, so we get this answer. Again, if you know the derivative of 3 to some power is natural log of 3 to that power, if that power is not an x, you have to multiply by its derivative. Let's find the derivative of something more complicated. This is about as complicated as we can make this. We have 3 to some power. What is that power? It's the tangent of something. Tangent of what? A square root. What's the square root of? X squared plus 9. Notice that the square root of x squared plus 9 cannot be simplified, so I have a fairly complicated composition of functions. The derivative of 3 to a power is the natural log of 3 times 3 to the power. The derivative of tangent is secant squared. The derivative of square root is 1 over 2 to the square root. In other words, the derivative of x to the 1/2 is 1/2 x to the minus 1/2. And the derivative of x squared plus 9 is 2x. Putting these all together by the chain rule, the derivative of 3 to that mess is the natural log of 3 to that mess times the derivative of tangent of that stuff is secant squared of that. What's the derivative of the square root? It's going to be 1 over 2 times the square root, but the square root is not just an x, so we have to multiply by the derivative of that. So there, we've done the chain rule composing, I think, 4 functions in a row, and then I can clean that up. We'll do some more of these in another slide.